Welcome to Module 8. This module is the first of 3 modules that cover beams. Module 8 is separated into 2 lessons. This lesson, Lesson 18, reviews the basic or general behavior of steel members subjected to bending. More specifically, the sequence of stress distributions are reviewed that develop in a steel beam as it is loaded and bending. The second lesson of Module 8, Lesson 19, will examine instability issues with steel beams. Whereas before, when we studied tension members and compression members, they were loaded axially. Beams are designed to carry transverse loads. The loading can be concentrated, distributed, either uniformly or non-uniformly, and also have applied end moments, which result in bending along the length of the beam. All these loads result in internal forces that the beam must be designed for, mainly bending moments and shear forces. We will see in Lesson 20 that we usually select the member size based on moment and then go back and check the shape for shear. And shear is covered in Lesson 22. Now, consider a beam that is subjected to pure bending. Obviously, bending or flexural stresses develop that are normal to the cross-sectional area. There are tensile flexural stresses on one side of the neutral axis and compressive flexural stresses on the other side. At relatively low load levels, the stresses will be linear everywhere, ignoring, of course, the presence of residual stresses. The stress distribution is governed by the bending formula, which you learned in Strength of Materials, and is given as my over I. If you don't remember the bending formula, then you really shouldn't be in this class. If we consider a rectangular cross-section and integrate the stress distribution on either side of the neutral axis, we arrive at both a tensile and compressive force. The magnitude of the force is given as the volume of the stress, or the area of the cross-section that the stress acts on, which is half the depth, or d over 2 times the width b, times the average stress, which is 1/2 of the maximum bending stress at the extreme fiber, or little f sub b. These two forces are equal in magnitude and act in opposite directions. They therefore form a couple, which is the internal moment that develops to resist the applied moment due to the loading. The distance between the two forces for this linear stress distribution is 2/3 of the cross-section depth, since the stress distributions are triangular. If you multiply the force by 2/3 the depth to get the internal moment and rearrange terms, you get BD squared over 6. This term is called the elastic section modulus, or capital S. You should remember for strength of materials that the elastic section modulus can be computed by the moment of inertia divided by the distance from the neutral axis to the extreme fiber, or little c. Note how the elastic section modulus falls out of the solution when computing the internal moment using the stress distribution. The internal moment strength is therefore given by the extreme fiber bending stress times the elastic section modulus. Values for the elastic section moduli are given in the section tables for both the x and y axes for all rolled sections, even though not all the rolled sections are appropriate as bending members. In the AISC specifications, Chapter F specifically, the moment capacity of a steel beam is defined by the bending stress that is present in the member at the instant of failure, or when the limit state is reached. As load is applied to a beam, the internal stress distribution goes through several successive stages beyond the simple linear stress distribution, as we will see. At each stage of loading, a different nominal moment capacity, designated as capital M sub n, can be defined by the couple formed by the stress distribution present at the time of failure. The normal or nominal moment capacity increases in value as the load increases. The nominal moment capacity will be limited by the exceedance of a limit state. The following discussion assumes an idealized stress-strain curve for steel. This is where the relationship between stress and strain is either perfectly elastic or perfectly plastic. This means that once the steel or the stress reaches the yield strength F sub y, it remains at F sub y for all additional strains. The first stage is where the stress distribution is fully elastic and occurs at relatively low load levels. We looked at this stress distribution before. The stress at any location can be determined by the bending stress formula, my over I, or for the maximum stress that occurs at the extreme fiber, or distance from the neutral axis, the M times C over I, or M over S, where S is equal to I over C. The elastic section modulus S can be used to define the moment capacity for any elastic stress distribution. It is important to note that the extreme fiber stress is used in this computation. As the load is increased, the extreme fiber stress will eventually reach yield. While the extreme fiber stress has just reached yield, note that the remainder of the stress distribution is still elastic. Therefore, the cross-section can actually carry additional load. The moment capacity at this stage can still be computed using the elastic stress distribution. Note that the stress value is now the yield stress, capital F sub y. We can designate this first yield moment capacity as M sub y. The computation of the first yield moment capacity in rolled and welded shapes is complicated by the presence of residual stresses. The residual stress pattern must be superimposed on the bending stress distribution. This causes the cross-section to yield early, since stresses are already non-zero in the absence of any load. It is assumed that the maximum residual stress in rolled and welded shapes is 30% of the yield strength of the steel. Therefore, yielding begins when the extreme fiber stress has reached 70% of the yield strength, or F sub y. In some of the design equations for beams, you will see the term 0.70 times F sub y times S, the elastic section modulus. This is the moment capacity at first yield considering residual stresses. In older versions of the LRFD specification, you see this moment capacity designated as M sub R, where the subscript R is for residual. Now, M sub R means the required moment capacity. However, in some of the beam design tables, such as table 3-2 for example, you will see phi M sub R, which refers to the design moment at first yield with residual stresses. Now, It is important to realize that, again, just because there is yielding somewhere on the cross section, it doesn't mean that the beam has reached the limit of its load carrying capacity. The load can be increased further since the inelastic regions can still resist additional stress levels. Stage 3 defines the inelastic region where a portion of the stress distribution has reached yield and is therefore plastic, while the remainder is still elastic. The plastic region is away from the neutral axis, while the elastic region is closer to the neutral axis. This inelastic stress distribution is still stable, and additional load can be carried by the beam. The nominal moment capacity can be determined by finding the moment couple for both the elastic and plastic zones and then summing the two together. If you throw in the effective residual stresses, the computation gets complicated. We will see that when we need the moment capacity in the inelastic region, we will use a linear interpolation function, which makes things fairly easy. Now, as the load is increased further, an ever-increasing portion of the cross-section yields until all the fibers have reached yield. Again, this is on both sides of the neutral axis. The fully yielded cross-section then defines the maximum moment capacity of the cross-section, as there is no more fibers to yield. This is called the plastic moment. The plastic moment is given as the product of the yield strength F sub y times what we call the plastic section modulus, or capital Z. The plastic section modulus is similar to the elastic section modulus S, but is based on a plastic or fully yielded stress distribution instead of a linear elastic stress distribution. The plastic section moduli are given for both axes for all rolled shapes in the section tables of Part 1 of the Steel Manual. Similar to the calculations we did for an elastic stress distribution, you can determine the moment capacity of a fully yielded rectangular cross-section by integrating the stress distribution over the cross-section and calculating the couple that forms. When doing this, the collected terms, other than the yield strength F sub y, gives you the plastic section modulus Z. Note that the plastic section modulus is 50% greater than the elastic section modulus for a rectangular cross-section. That is, you have 1/4 versus the 1/6. This means that the nominal moment capacity is 50% greater when based on the plastic state versus the elastic state. And again, that's for a rectangular cross-section. Now for an ice-shaped cross-section like W shapes, the increase from elastic to plastic moment capacity is between 10 and 15%. Shown in this slide are calculations for the plastic section modulus Z. The upper formula is using the full outside rectangle and subtracting out the plastic section modulus of the area that is not there, similar to what we saw for moment of inertias. In summary, when a beam is loaded, the internal moment in the beam goes through 3 regions of behavior and 4 distinct stages. Shown is a plot of the nominal moment capacity versus the beam deflection. The 3 regions of behavior of beam are elastic, inelastic, and plastic. It is important to note that the maximum or ultimate bending strength of a steel cross-section is given by the plastic moment capacity, or M sub P. This gives you the upper limit on the moment capacity as the cross-section is fully yielded and no additional capacity is available. Therefore, the plastic moment, or M sub P, is a limit state for beams. Since the maximum moment capacity of a steel beam is defined by the plastic moment, it is highly desirable to have this as a design limit state. This means the cross-section will be fully utilized as it will be fully yielded. This is called the yielding limit state. However, as will be discussed in Lesson 19, it will not always be possible to reach the plastic limit state due to the exceedance of other limit states based on either global or local instability or buckling, meaning the beam will buckle before the yield limit state is reached. If the plastic moment cannot be reached prior to failure, the moment capacity is then defined by the stress distribution at the time of failure. Therefore, the stress distribution will be either inelastic or plastic. This ends Lesson 18.